everybody. So today I'm going to mostly talk about galaxy formation, since yesterday I talked a lot about dark matter. But let me begin with a little bit of history. Okay, so I try to summarize all that's happened in cosmology after the discovery of the expanding universe, basically, pioneered by the work of Friedman, Lemaitre, and Hubble. Okay, so and so this is the period from, say, 1933 to 2000. So briefly, quite early it was realized that dark matter is present in the universe, matter that we don't see according to our application of Newtonian Einstein gravity in clusters and in galaxies. And all of this has later been confirmed in immense detail, of course. Let me just point out that Vera Rubin, who just died a few months ago, pioneered the dark matter discovery in M31 using optical data, and it was with 21 centimeter data that one went much further out and really confirmed that the galaxy was dark matter dominated. Then another early development was by Gamow and his various collaborators on primordial nucleosynthesis, in which helium and deuterium especially can be explained only really by the first minutes of the Big Bang, with a question mark still hanging, interestingly, over lithium, which the Big Bang does overproduce when you normalize to helium and deuterium by a factor of 3, and that factor of 3 has simply not gone away over the years. Most likely it's a stellar astrophysics problem in settling and destruction of that excess lithium, we think, but the details still have not been worked out. So that's maybe the one slight shadow hanging over the whole theory, I would say, still from the early years. The cosmic microwave background, a major discovery, and the spectrum of a perfect black body. Okay, so probably a more precise black body than one can even measure on the Earth is now seen in the sky, thanks to the COBE satellite Michelson interferometer that was used to measure the spectrum. Black body to a precision of 1 part in 10 to the 4th, actually. Inflation, pioneered in the 1980s. It's interesting that the field of cosmology was developed by astronomers in these early years. It was with the advent of nuclear physicists that primordial nucleosynthesis really exploded, began and exploded. And it was with the advent of the particle physicists who realized the universe was a wonderful laboratory for high energy physics that they could not achieve on the Earth, that from those ideas, the idea of inflation emerged, which explains not just the size of the universe and its spatial curvature, and dominance of dark matter, incidentally, but also the fluctuations. Then the whole application idea that the dark matter had to be intrinsically cold, so it was unstable under gravity, was developed gradually by particle physicists and astrophysicists. And there are candidates like ultralight particles called axions, and the heavy particles, the WIMPs that I talked about yesterday, predictions of the theory of supersymmetry, which still has not been confirmed at the Large Hadron Collider, but nevertheless it's one of the best predictions we have for dark matter. And all of this constituted cold dark matter, which gave a wonderful fit to the large-scale structure of the universe. And that in some sense, arguing backwards is indirect evidence that cold dark matter is a good assumption, because one can fit now not just the early surveys, but the modern surveys of millions of galaxy redshifts with the structure of the universe, with the hypothesis of cold dark matter. Then the acceleration was measured by 2 groups. and sort of pretty much confirmed by the year 2000. And that led to the introduction of the cosmological constant, which had been speculated a lot about, introduced by Lemaitre even, but this was evidence for that. The microwave background anisotropies were pioneered soon after the discovery of the microwave background, but confirmed beautifully in the early years by the COBE satellite and by balloon experiments, and more recently by, of course, WMAP and Planck and so forth. Large-scale structure, we're now in the epoch of more than million-degree galaxy surveys, but in these years it was the 2DF survey and the Sloan Digital Sky Survey that gave us our first insights into the large-scale structure of the universe. It's interesting that you just need surveys of vast numbers of galaxies to understand much better a single galaxy. It's only by statistically looking at galaxies that you can pick up this information that you otherwise would miss. You know, it's a bit like when you do medicine and you study epidemics that break out. It's statistics that make all the difference. And even when an individual doctor analyzes your particular illness, it's only his experience with many other patients that allows him to diagnose what might or might not be wrong with you. And then finally, galaxy formation theories, and that's what I'm going to mostly talk about today. Okay. So, acceleration, just to summarize where we are now. So what is truly impressive about the Hubble diagram, redshift distance basically, is that the idea of the expansion law was pioneered. These Hubble and Lemaitre 2 years before him first analyzed the data at that time, the very crude data, and deduced the universe. There was a relation of redshift and distance, which is now interpreted as the expansion of the universe, but that's in this tiny part of parameter space out to maybe 1 megaparsec or so. And since then, we've gone out to the horizon, basically, to redshifts of 2, and measured this linear law of expansion with now the discovery that the dashed line is the linear law, and the deviation from it with all the data is the evidence that we live in an accelerating universe, that just at rather recent epochs, the universe is beginning to accelerate. And you can see this is a fit to what we now call the standard lambda CDM cosmology. Okay, so how do we explain that? So first, just a brief word on the inflation theory, because that's really the beginning of the galaxy formation story. So let me just explain the basic that we need for that. So this is the Friedmann equation, Friedmann-Lemaitre equation, in which the acceleration of the universe, there's a source term, which is the energy density, basically. And it's the density, but in general relativity, pressure exerts gravity as well. And so this 3p comes only from general relativity. If you go through Newtonian cosmology, you basically would just have a rho in there, which is fine for giving you the simple models of the universe, but does not allow you to understand the acceleration. So the way the acceleration can be explained is, of course, if a double dot can be positive. And the only way you get to be positive is by introducing a negative pressure. And so we have a very simple way in particle physics of introducing this negative pressure by hypothesizing a new scalar field, okay, which is indicated by phi. And this scalar field, you can think of it as a new type of particle, if you like, or whatever, but it's really a field with energy. It has energy, it has kinetic energy, potential energy. So the equations of the density in the scalar field are the sum of kinetic, phi dot squared, plus potential, and pressure is phi dot squared minus potential energy, okay? And so you can see that if you want to have negative pressure, then all you need to do is invent a scalar field that doesn't change or changes very, very slowly. And that's the basis of inflation. So what does this scalar field look like? Here's the potential energy curve of the scalar field. It basically is very, very flat. And this then gives you a period when a double dot over a can be constant, because the potential is essentially constant. And so basically, these two terms balance out, and you get, and if a double dot a is a constant, then the only solution to that equation is an exponential solution. The scale factor goes as e to the ht. Okay, so it's as simple as that, and this then But of course, this potential is slowly progressing as the universe is expanding, if you like, and eventually will fall down develop more kinetic energy, and so the pressure comes back in, and when you develop more kinetic energy, these terms come back and the inflation stops. And so and inflation ends over here, and we say that the potential, there's some oscillation of kinetic energy which reheats the universe, and you reduce to the normal universe. Okay, so here's the picture that you get from this. There was a period of inflation early on of expansion. This is the last galaxies of the background. These are the structure formation, the dark ages, and then, which I talked about yesterday. And what you have to remember, you may say, oh, this is just a house of cards. I'll try to explain why next, why we think there is some good reason to believe some of this stuff, is that here we have the late acceleration. Okay, so this is the cosmic constant causing this, but this is what we've measured now. Convinced ourselves enough to give out a Nobel Prize, okay, for this acceleration. And here we have a similar phase where inflation occurred. Of course, the scalar fields are very, very different. Here, the energy that drives this is very, very tiny. We call it the cosmic constant. But the fact that we very much accept this, as I'll try to explain to you, as a fundamental property of nature, most of us do, means that we shouldn't necessarily argue that we need very special circumstances to understand the late acceleration of the universe, namely the smallness of the existence of a cosmic constant. Okay, so that's just a bit of, philosophizing maybe, but why is inflation such a good theory? Well, it made three predictions, basically. It told us that space was essentially Euclidean. It explained why the universe is so large, and it gave us primordial density fluctuations. So now, why do most of my colleagues trust inflation? There are always some people that are skeptics and will, basically say, no, it's just too much of an assumption. There must be something else. But it's a theory that's done a lot for us. So first of all, it produces these density fluctuations, which seed the galaxies, and they're coherent in phase. So here's the power spectrum, basically, the temperature fluctuations. And these peaks demonstrate phase coherence. And the fact that when you look at the polarization, you can see that that is beginning to give you, and this corresponds to the horizon of the universe, 380,000 years after the Big Bang. That's when you can see the first temperature fluctuations. The fact that the polarization is slightly out of phase is telling you that these things were on super horizon scales, basically, and were basically explain why the universe has fluctuations in it that once maybe were acausal, because they would have been outside the present horizon if I go back early enough. It's a wonderful prediction, and an explanation too, I think. And finally, here are the more specific predictions of inflation. The most specific one today, it predicts the fluctuations have a certain distribution of scales, of strength versus scale, and it tells you exactly what that should be. If n is 1, it's totally constant. Just one number explains everything, but it's not. And inflation says it can't be exactly constant. There must be some slight variation. And this is what's measured by the Planck satellites. A many sigma deviation of the scalar index from unity, namely a slightly rolling fluctuation spectrum in amplitude, very, very weakly. This is a prediction of inflation. Now, unfortunately, inflation doesn't. There are many versions of inflation. They don't give you a precise value. So we're still looking for other tests of inflation, okay? And here are two. One is fluctuation should be Gaussian. That's sort of a generic expectation from inflation models to a high level. And so far, we've measured Gaussianity with the Planck satellite to better than 0.01%, okay? Now, at some level, if you can go to much more precise data, you might expect to see a signal, but this is a prediction of inflation. And finally, there's a prediction there should be gravity waves, which leave their imprint on the microwave background. And right now, the current limit, upper limit, is less than about 10%. Okay, so we're hoping in the future to do much better, to measure a gravity wave signal. As I said yesterday, there's no robust proof that has to be there. But the fact that inflation does so much for you, now, you can see you don't have any definite proof that inflation occurs. You can't point to one number and say, aha, that's inflation. It's not as though you're measuring some, Planck's constant or something, and that's a number that you measure. Inflation's different. It's a whole class of different theories, but the fact that it explains so much about the universe gives most cosmologists high confidence that it exists. We're sort of all Bayesians at heart, and in some sense, if you have enough reasons, both theoretical and experimental, that the theory is doing something right in terms of the data, that means you can trust the theory, that it's a good theory, okay? You haven't proved that it's correct, though. So it's very dangerous to say that inflation did occur. You can never be sure, and maybe we'll never be sure at the 99.99% or whatever, that it did occur, but I think there's reasonably high likelihood that it did occur. That's my view on this. Okay, so moving on to the main thing for the purpose of galaxy formation, what inflation did for us. This is the story that imagine the universe expanding, the horizon expands at the speed of light by definition, right? And imagine the mass that is going to form a galaxy eventually. There's some inertia that's going to make the galaxy. It's a density fluctuation, right? And therefore, it can't expand quite at the speed of light, right? So if I track this region back in time that tracks some specified mass, if I go back in time, it's going to be outside the horizon, okay? And in classical cosmology, back in the 1930s, there was no way of understanding this. One had to say, this was how the universe was, okay? But inflation has come along, and because of this exponential expansion, allows us to assert that here are quantum fluctuations, which are imprinted on all, on small scales, and they're exponentially boosted to very large scales, and later come inside the horizon. Okay, so that is a very beautiful and elegant explanation of the fact that structures are there, not just the imprint of their amplitudes, but they basically the fact they would have been a causal, we get around that. Okay, so that's all I'm going to say about inflation, but it does imprint these seeds. So what do you do with these seeds? And so the way that works is you go to the theory of density perturbations in an expanding universe, okay, and that's sort of a classical problem studied initially by Lemaitre, by many people since, and basically you're solving the momentum equation, the continuity equation for mass conservation, and Poisson's equation, right, for perturbations about the Friedmann-Lemaitre universe, and this is the equation, second-order equation you get for the density fluctuations. So the first comment you have to make is, if A dot is the scale, A is the scale factor, and A dot over A is the Hubble constant, right? So if the universe is static, A dot would be 0, there'd be no rate of change, and this term wouldn't be there. And then I'd have a second-order equation in which there's a source term which is gravity, self-gravity, and over here is the effects of pressure, okay? And basically, if the gravity term dominates over the pressure term, in the limit of a cold universe, this would be negligible, right? Then I get exponential growth of fluctuations, okay? But as soon as I put in the Hubble term, the expansion, then the fluctuations stop growing exponentially, but now just grow slowly with time. And this is why inflation is so important, because it gives you the initial conditions. Otherwise, you could never understand the seed fluctuations which galaxies were made. So here's the solution to this equation, very, very simple, in the limit when I can ignore the pressure term, okay? And the solution is just very simple. It says that the density fluctuations, this is the matter density, the radiation density. Remember, the matter density by conservation of mass goes as 1 over scale factor cubed. Okay, the smaller the scale factor, the higher density. Whereas the radiation, because the energy of the photon red shifts away, goes as inverse scale factor to the 4th power. So this term goes as scale factor. So in the limit when I'm radiation dominated, nothing happens, constant fluctuations, no growth, because you're radiation dominated. But the limit when I'm matter dominated, and that's after redshift of roughly 10,000, I get growth of fluctuations, but at a rate that just goes as 1 power of the scale factor. So that's really all there is to structure formation theory, okay, to set up the scene, except that this is linear theory, right? So then the question comes, how do you make this all nonlinear? And so the first step you do is, this is what Lemaitre originally did, you consider the expanding universe, and then you consider a shell of matter, which obeys the same equation as the expanding universe, but it's over-dense, and that shell eventually is going to contract and collapse, in principle, to a point, okay? Unless I put in pressure effects or if I allow it to lose energy. But in practice, if it doesn't lose energy, it's going to bounce around and end up at 1/2 its maximum radius. Okay, so that's a simple application of the virial theorem. You can easily show that this radius at which it ends up corresponds to when the halo density is 18 pi squared times the density of the universe at this point, which is the maximum size. So if you measure the density of a halo, you can infer when it formed, when it first detached from the universe. Okay? So that of a dark halo, because the dark halo is matter that hasn't been able to radiate and collapse all the way down to a compact thing. And this is true then for something that can't lose energy, the spherical shell approximation. Obviously, I'm assuming a spherical symmetry, but it's, this actually is not a bad approximation to all we do with dark halos and galaxy formation. Okay, we can measure the dark halos or infer them. So that's one nonlinear extension of the theory. And then the second one, which is fundamental to modern cosmology, is called the Preshektor theory. And that simply says that any fluctuations above a certain threshold value, which corresponds to this, will collapse. And because there's always going to be some exponential tail to your distribution of fluctuation densities, some dispersion, then at any given epoch, some will collapse. Okay? And then as time goes on, larger and larger fluctuations can participate, which have lower densities, can eventually reach that threshold and then collapse. So what this very simple theory predicts is that if I look at I can calculate with some distribution of density fluctuations what the fraction that goes nonlinear is. It's above some threshold, and then you can show that early on you get a certain distribution of fluctuations, which have now become halos. These are fully nonlinear, and as time goes on, larger and larger ones participate, and eventually I end up with this, and this is the mass function today of dark halos, if you like. Okay, and the generic prediction is that this tail always goes as 1/mass squared, the number, which means you get a lot of very small objects. Okay, and so that's generic to cosmology. And this is one of the biggest problems in modern cosmology. It generically predicts lots of very small dark halos, which in principle should contain baryons, which in principle should cool down and make stars, and we don't see very many. So this is one of the big problems. Okay, we'll come to that in a minute, but before then, the connection, again, final connection between the microwave background and structure formation. So here is what I talked about, this straight line, which corresponds to scale invariant fluctuations, constant metric fluctuations. And then as time goes on, when in the matter era, they can grow. Now, because the matter era commences when the horizon was fairly small, it's only the smaller ones that have maximum growth. And as time goes on, the larger and larger ones enter the horizon and become causally connected, can grow under gravity. And so this initial simple ansatz about scale invariant fluctuations, inflation predicted, if you like, then turns into, it's filtered, if you like, transferred into a spectrum of fluctuations that basically has smaller values on larger scales, okay? We call this bottom-up formation, okay? Small things form first. And so these are things that make the first galaxies, and larger ones form, and the largest superclusters are somewhere over here. So the amazing thing is that this turquoise line is a more accurate representation of this curve, okay? And the microwave background data, those are all these red points, fit exactly on this curve, and we try to estimate from galaxy clusters and various other things where those data points may be. They all fit this curve. You can estimate what, as I said, from their mean density of a galaxy, you can figure out roughly when it formed, from an estimate what its amplitude is in linear theory, okay? And so all that we know seems to agree with this picture in which these things form first, and as time goes on, larger and larger forms. And we're measuring all the fluctuations in the microwave background that fit this theory. So it's an amazing, I think, another amazing piece of evidence that gives confidence in inflation, if only because the rival theories to inflation cannot, as far as I know, predict anything as precise as this. Okay, and in fact, they have many of them have singularities and various things. Okay, so that's the general background. Now let's get into the actual physics of what is a galaxy. Okay, so there are basically two forces, two physical processes that come into action here. One is gravity, which causes a cloud. Let's imagine we have a cloud in a dark halo full of baryons, some fraction of baryons, 1/6 by nucleosynthesis initially. And so the baryons can lose energy and dissipate, and gravity will control their collapse time. So the key physical processes are the rate at which you can lose energy, I call that the cooling time, and the free fall time. And so that controls how rapidly you can make a galaxy. Now, efficiently, that cloud can then turn into stars. So I'm just going to compare these two timescales. And so the basic bit of physics that you need is the atomic cooling curve for a plasma of hydrogen helium, because that's really all you have before any stars formed. Okay, and so that's characterized by, I'm ignoring molecular cooling. This is temperature. This is the cooling rate per atom. This is the Lyman alpha peak, and there's a helium peak. Okay, and then bremsstrahlung comes in. And so what you can do now is you can estimate the cooling time. The free fall time is 1 over square root of g rho, right? And the cooling time is the thermal energy, Nt, divided by this cooling function times its a binary process, n squared, okay? And so the upshot is that if I set these two times equal, just to give me a critical estimate of what's going to happen, you get this condition that density must go as temperature squared over lambda squared, okay? Just by setting these two equal, okay? You can see that. Okay, so what does this mean? Okay, well, let's now translate this into the real world. And so this curve, this red line, is roughly the inverse of this. It's 1 over lambda squared times t squared, okay? That's what this red line is. So it's a critical condition, and above the red line, everything can cool in less than 1 free fall time. Outside the red line, it takes longer. And so let me hypothesize that the condition to cool in less than a free fall time is necessary for making stars efficiently. Okay? Seems reasonable, right? Just a plausibility thing, if you like, okay? It turns out now, if you go to the real universe and you try to estimate what the typical densities and temperatures are, temperatures from the virial dispersion, right? Velocity dispersion, should be gas shocks, whatever gives you a temperature. You find that the clusters and the groups lie outside. Their cooling times are rather long compared to the free fall times. They may be less than a Hubble time, that's fine, things can happen, but they're inefficient for making stars. So massive things don't make stars very efficiently. They contain galaxies that do make stars. But all the galaxies I know from the early types, which have obviously are very dense in the center, so they have undergone a lot of dissipation, they're high up on this curve, and the less dense things, they lie within this curve, and so we presume we'll be making stars. And so this black line is the trajectory from the inflation theory of fluctuation, starting off with dwarf galaxies, which have low velocity dispersions, working their way out with time as the universe. So this is roughly redshift 10 over here, when you first enter this cooling curve regime, when the first galaxies could be made. And then today, redshift 0, when the large structures are assembling. And so all of this stuff that we see lies inside this dissipation area. So this is the physics behind gas dissipation, which is the key to understanding why galaxies are what they are, okay? And so if you can try to make this a little bit more quantitative, and this is the argument. And so, so this red line is the pressure theory, which has lots of small things, and because things can keep on accreting on a Hubble time, I get lots of big things too. And these are the observations. This is the Schechter luminosity function, basically. And at first sight, you get very depressed and say, there's absolutely no connection between the two, except maybe they can overlap at one point. And so let's take that for the moment as something good, okay? And let's try to estimate what the physics of this one point where they do match might be by forcing the red line, which is theory, to meet the blue line. So here's my cooling time, again, nkt over lambda n squared. Here's the free fall time, 1 over root g rho. I set the two times equal. I ask, what is the critical condition for effective dissipation to occur? And that turns out to give me a critical mass in terms of fundamental units, okay? Alpha is the fine structure constant, and alpha g is what we call the gravitational fine structure constant. It's the ratio of the force of gravity electromagnetism between two protons, in fact. So the details don't really matter. The main point is that there's a very weak function of temperature left behind, and this is basically a number which turns out amazingly to be of order, give you of order the right mass to luminosity. The ratio between these, this is dark mass, this is luminous matter, and I can get roughly the right ratio for this typical mass of cool baryons, which translates to being the mass of a typical dark halo, the mass of a typical luminous galaxy, at roughly what we call the Schechter point, the Schechter luminosity, which is where these two curves match, at roughly 3 times 10 to the 10th to the luminosity. So we think this simple theory can explain the typical mass of a stellar mass of a galaxy. How you get rid of all the small ones is a subject of great debate, and the favored mechanism is having lots of supernovae occur, and because they're effective in very small galaxies where the escape velocity is quite low, then repeated explosions of stars made in the initial gas can drive most of the gas out before it's had time to make too many stars. So you have very, very low efficiency star formation in the smallest galaxies. You'd expect that just from having a standard initial mass function of stars. For the big galaxies, that doesn't work very well. There you need something much more powerful, and the current favored candidate is the supermassive black hole, and this gives you a cartoon of how that works. So as stars are forming out here, in the dense part of the galaxy, we presume the collapse time, where it's much shorter, would allow you to form a supermassive black hole. The details are very obscure, but we see these things in essentially all galaxies. And that black hole, when there's lots of gas around it, will accrete matter from a circumnuclear disk, drive a huge outflow from this energetic release near the horizon of the black hole, and that will then sweep the stuff out maybe and give you enough feedback to kill off these galaxies. So I'm now going to talk a little bit more about the details of how all this works, but basically, these things, these ultra-faint dwarf galaxies, are the sort of things you might naively expect would be the relics that you haven't completely destroyed. This is a more typical galaxy where in galaxies like this, it's the supernova feedback that has mostly kept this one pristine. And for the very massive galaxies, then inside a galaxy like this, there is a very supermassive black hole, and that these may be vestiges, if you look at very low light levels, of what it might have been long ago if those are stars. We don't know for sure, but they may be residues of mergers or whatever, but that's the sort of thing you might expect. So this is the way the theory sort of can then be applied on the cosmological scale. So this is a simulation of a large box, a 100 megaparsec box of the universe from redshift 3, 2, 1, 0. You can see structure forming, and the color coding is a rough indication of the aging of the stars. And so the first galaxies that form are in the densest regions, and as time goes on, they become red, and you still have lots of yellow, which means younger things in the outer parts. So this is qualitatively how we see structure in the universe, and this is a more modern zoom-in simulation, which shows you how, if you try to, you can understand this large-scale structure from very cold accretion that naturally gives you these large filamentary-like structures, and then as you zoom into an individual galaxy, the simulations give you something that looks beginning to resemble galaxies that we see. But the problem with this is that this is 100 megaparsec scale that you start with these simulations. We're now discussing here not just a few kiloparsecs, which is the region of the center of the galaxy, but to understand star formation, we have to understand what goes on in astronomical unit scales, right? That's millionths of a parsec, and no simulation has that dynamical range. And so basically one uses what's called subgrid physics, which is based somewhat on local phenomenology, which may or may not be good. Okay, yep.
What are the colors in these simulations?
Okay, so they're in this simulation it was age, and in this one it's feedback actually. So the red stuff is indications of the very hot gas being heated up by the, and so here, and combined with some star formation maybe. And here there's no color, so it's all old stars is the claim. Yeah. Right, so I'm now going to give you the positive and the negative aspects of this. So the first positive aspect, and unfortunately it's probably the only really positive aspect that I'm going to draw on, is this one. So this I think was an incredible discovery at the time, and we're now finding more and more of these objects. These are ultra-faint dwarf galaxies. And qualitatively, it's just what you expect from the cold dark matter theory, okay? The fact that you have produced so many dwarfs and you have to destroy them, there should be lots of relics left behind. And this was a few years ago. We had maybe a dozen of them around the Milky Way, and now we're finding many, many more of these things, right? And I don't think we really know how complete the numbers are yet. Okay, so that seems to me the one thing you can say, aha, the theory predicted that, and we're finding them. Now, whether you have enough of them is another question, okay? But this is going in the right direction. Okay, so, but since all of you, the students at least, are want to write PhDs, so it's good to have problems, right, that you want to solve. So I'm now going to tell you about the problems with the galaxy formation theory, and I should warn you there are many of them. So let's begin with star formation, right? And so turbulence is an ingredient that's not usually put in the criteria for making stars in the cosmological simulations. And the reason is it's complicated, and it's so far almost all the simulations use a density threshold and a convergence condition and velocity flow, and say that something is dense enough and flow is converging, then I will have the element make stars. It's because you can't resolve in detail the actual size of star formation. But we know now that turbulence is a crucial thing to add. But it's unclear at the moment because that can obviously give me extra pressure that can resist gravity, for example. But if you look around in the universe, you find that, fine. In the center of the Milky Way, we have a giant molecular zone where star formation is suppressed, okay, to some extent. It lies very low if you try to apply the Schmidt-Kennicott law to the center region of the galaxy. And it's true also in barred galaxies. There are regions in the center which are very, very weak in forming stars. So you'd say turbulence suppresses star formation, right? And therefore that's what you should put into your black box, your subgrid physics for star formation, critical to the cosmology simulations. Okay, the trouble is you can now point to another region studied with ALMA. One example is a starburst, a dwarf starburst, NG253, where you find, lots of turbulence in the center, as seen in many molecular lines. And you find that if I compare this galaxy to the Milky Way, that despite this incredibly high Mach number here, so we're talking about really supersonic turbulence and higher densities, star formation is enhanced. So that the point of this is to show you that we don't even know the sign of the effect. And one of the interesting ideas behind this is that if I have some distribution of densities, and I ask, this is the PDF of density distribution, and in a simulation you ask, where are the stars forming? Well, if there's some tail to the density distribution, then these are regions that are very dense, and so maybe more unstable, it could be forming stars. So you have to be able to address in your simulations, not just the typical distribution, but the rare tails, which might control star formation. That might be why star formation is inefficient. And this is just fine if you want to focus in on one cloud or even a small part of one galaxy, but to combine this physics with cosmology is very challenging. Okay, so that's one comment. Right, so here's another worry about the whole field. So a recent study with one of the leading codes for doing cosmological simulations used different criteria for supernova feedback. That's what I argued was critical in explaining why we see very few dwarf galaxies. And so I'm not going to explain in detail what they're doing, but so they tried 5 different recipes, one with no feedback, all of these with various types of feedback, in trying to make disk galaxies. And they found that none of them worked, basically, and the way you test this is you look, for example, this is This is the Schmidt-Kennicott relation, star formation rate versus mass. And so they found that their models either were low or high, and basically nothing worked. Okay, so, right. Okay, next problem is this is a comparison of all the theories to date with their predicted luminosity functions, actually masses of stars, right? And so these are many different simulations, and you can see they simply do not agree with each other, right? So there are just, they have different feedback recipes, and so the problem is that the numerical simulators cannot really agree. You know, orders of magnitude separate what their models predict, so we don't know, okay? Next, the number density of dwarfs, okay? So here is the observed number density, right? These are local group galaxies, okay? And this is the simple model of dark halos. And so when puts all this into simulations, this is one of the more recent results. The claim now is that whatever feedback you use, you're completely unable to explain the low number you see. So this is basically what the wide range of different feedback recipes seem to predict. This is what they want to get to. So they're predicting too many dwarfs at these low circular velocities by a factor of a few. If you go down even further, far more maybe, but basically this is a range you have to worry about. So these are dwarfs that are quite accessible. So these are circular velocities of say 20 to 50 or 60 kilometers a second. You know, there are several times more in the simulations than we actually see in nature. And so it's a problem. It just proves that we don't understand in detail how the feedback works. Okay, going on. So we've now finding, well, I mentioned these low surface brightness dwarfs. We're now finding new classes of galaxies, the ultra diffuse galaxies. And so these are now being seen in groups. So these are snapshots of these things at incredibly low surface brightness. Are they remnants of feedback? We don't know. But we're finding giant versions of these ultra low surface brightness galaxies too. This one has 100 globular clusters, for example. So although now it's not that massive in terms of stars, with 100 globular clusters, it probably was with the relic of something much more massive. And so we're pretty sure that supernovae cannot explain these examples of ultra diffuse galaxies. It may work for these when the object was more gas rich and was making stars for the first time, but it's not going to work for these more massive examples. So again, we're missing something. Here's another example of what supernovae cannot do, nor can black holes do either. These are galaxies with no supermassive black holes. Okay, so as far as we can see anyway, because the bulges are really tiny. Okay, and so these are remarkably bulgeless galaxies. And again, the theories of all the simulations inevitably have some angular momentum loss in the collapsing baryons, and it's very hard to avoid making a bulge. In fact, in the early days of simulations, they were making the bulges were too big. But now we're finding objects, that problem's been solved now, but now we're finding objects with essentially no bulges at all, and I would say it's very, very hard. No one has yet figured out how to make these. Okay, so more problems. I've got about two more, I think. So this has been called the too big to fail problem from the simulations. And so the shaded areas where the dwarfs are, and you know, one is finding a certain number of dwarfs, maybe not too many if you put in the right feedback. But the problem is the same simulations predict dwarfs in another region. This is circular velocity. So these are dwarfs of intermediate mass, and these are simply not seen. Okay, they're massive enough so they should have enough gas to form stars. Supernovae do not drive the gas out. They're too massive for that, and yet they're predicted. We simply don't see them. And so this has been called the too big to fail problem. There's no consensus on how that works. That's solved either. It's debated hotly. Then there is another famous problem. This is the last one I'm going to show you. This is called the core versus cusp problem. Okay, so in the standard theory of cold dark matter, the dark matter has a cusp, a so-called Navier-Frank white cusp of roughly 1/r in the central regions, which you could see by the rotation curve, right? So this is the slope that you see, and this is the prediction of that theory, and this is what you measure. And so there's a wide range of the measurements, but most of the dwarf galaxies basically simply do not show evidence of a flat isothermal core, but not a cusp. Okay, so again, you may hope that feedback could solve this. It doesn't. Warm dark matter has been appealed to as a major solution, because warm dark matter basically cuts the power off in the spectrum at roughly the scale of a dwarf. And so if you have less, basically, maybe that would suppress enough power to give you a cusp, because there's no power on smaller scales, so there's no fluctuation, so maybe that naturally give you a cusp. So again, the latest studies show that's wishful thinking, and so here is all these. This is all data. Okay, this is circular velocity versus scale. Okay, so these are rotation curves, and you can see that cold dark matter is a complete disaster. Okay. Warm dark matter in various simulations doesn't give you the trend either, and so in this particular study they went to something even more exotic, something called strongly interacting dark matter, which is dark matter with a huge cross section, interacts with itself, and therefore suppress structure more effectively than warm dark matter, and they would claim that's giving them something closer to this, but even then it doesn't look perfect. And okay, and then finally, my last problem is called the cosmic baryon fraction problem, and that's this. And so if you look at nearby galaxies, the Milky Way is a great example. You find that there's roughly half the baryons predicted by primordial nucleosynthesis. Okay, and so these are the missing baryons and with individual galaxies plotted that have been measured. Okay, and others estimated. In galaxy clusters, there's no problem, okay? So in galaxy clusters, if I add up the baryons, this is the prediction from primordial nucleosynthesis. I get a certain baryon fraction. And in the most massive clusters, I'm pretty much up there. As I move down towards groups, right, I'm beginning to see a little bit less. These are error bars on these points from X-ray observations. But in galaxies, it seems to be a real disaster. So you may say, why can't feedback of some sort work? Well, the problem is that supernova feedback, imagine how could that work? Well, you might hope that although it can't work in the Milky Way, it probably wouldn't drive the gas very far. What about when the Milky Way assembled? We think the Milky Way formed from a large collection of dwarf galaxies, right? So maybe the supernova in these dwarfs could drive the baryons away. That doesn't work either, because the supernovae can drive baryons out, but not far enough to escape the virial radius of the final galaxy. So we are pretty confident that we have no solution to this particular problem. Okay, let's see. So how am I doing for time?
10 minutes?
10 minutes, okay. Right. So let's now look at one proposed solution, supermassive black holes, to many of these problems. And so the way that works is basically this is the Eddington luminosity. We think this describes the luminosity at which, and it's, remarkably, it just depends, it's a relation between gravity and electron scattering determines the maximum accretion rate that can fall onto the black hole, and you can translate, and that gives you luminosity basically, so it's only on the mass of the black hole, and fundamental constant. So that's interesting, and so you can now compute the possible effect of all this luminosity on the matter around it. So one thing you can do is compute the radiation pressure, that's L over C, and compare that with self-gravity. And you can also use this to compute the outflow from winds or whatever. It turns out to be closely related to this momentum input from radiation, which controls everything. Anyway, if I compare these two, then the self-gravity, you notice, is just gm squared over r squared. And so here I have a black hole mass hidden inside L Eddington. And inside gm over r, that's sigma squared, the velocity spread of the galaxy. Let's assume it's an elliptical galaxy. And so I end up with a prediction that the black hole mass should go as sigma to the fourth. And the amazing thing is, if I put in all these numbers, which I know perfectly well, the proton mass, Thomson cross-section, here's the normalization you get. It says that for the black hole mass, and if I have a black hole more massive, it will blow the gas out, that's the idea. The Eddington numbers will be high enough to get rid of the gas. So I should settle down at something like this relation, that's the claim. And that's where this relation between black hole mass and sigma saturates. Otherwise I get blowout and I would stop star formation. Okay, so what actually happens in practice is, these simple arguments actually can give you all sorts of interesting properties of supermassive black hole feedback. You can estimate from this radiation output what the effective momentum is for the Eddington mass flow, and that gives you an effective wind velocity of 1/10 of c, which is roughly what you see in the inner parts of coming out of the black holes. All that works nice, but here's the evidence that gives one some confidence that this simple argument can't be too far wrong. So this is a plot of black hole mass against velocity dispersion for round galaxies, basically, and for the bulges of galaxies, I should say. And so you can see that over some huge range of black hole masses, from 1 million solar masses up to 10 to the 10th solar masses, one more or less obeys this simple scaling relation, which tells you the black hole mass, the black hole, knows something about the stars, right? The old stars. These are old stars in the spheroids. So we think they probably all formed at the same time. Exactly what set up this correlation might be this feedback argument I just showed you, or it might be something else, we don't know. But this at least is circumstantial evidence suggesting that there was a fundamental connection between the two. Okay, right, so let me tell you, I'm going to spend my last few minutes telling you about, a little more detail about the feedback and showing you one or two simulations. So how in detail does this work? Okay, so you have jets. We see jets from these very energetic black holes. We also infer the radio loud quasars and radio quiet quasars. We see evidence of powerful winds. And again, from the Eddington luminosity, you can estimate radiation pressure. You can convert that into momentum. And so here's an example of a recent simulation in which one basically can, so you don't know the coupling of these outflows, right? So there are two simple assumptions that people make, okay? One is that they balance momentum against the intervening gas, or that energy is conserved, okay? Okay, so you may think momentum balance is the simplest thing. It is the simplest thing, the most logical thing, but it turns out to be wrong, because it just isn't insufficient to eject enough, to transfer enough momentum to the surrounding gas. And what you're trying to do, ideally, is to quench the star formation, to drive the gas out. So momentum balance cannot do that. And in this simulation, they showed indeed that, sorry, I've said, you're right, that when you go to energy balance of this outflow, then the energy basically, if that's conserved, you can see that means the momentum, mv, goes as 1 over v. So if you have energy conservation in the outflow, as the thing expands, you acquire more and more momentum, which gives you this immense push, and that can drive the stuff out. So that's the way we think quenching works. The only slight problem with this is that even in their momentum driving configuration for the simulation, you can see gas is coming in dense filaments. So they don't actually stop star formation completely. So this is an unsolved problem too. But the nice thing about this is if you look at the data, you find there's now interesting evidence. And so this is an X-ray observation showing you ion line absorption, measuring the velocity basically, inferring it's 1/10 of c in the central part, right? And you can now connect this nuclear blast from the central quasar to the cold gas outflows far out, and you can find that indeed energy conserving works, momentum goes up and up, and can drive the outflow. So this means that we just have two examples of this so far. We've been able to connect the inner speed with the outer speed, 1/10 of c to a few hundred kilometers a second, but that is enough to suggest that we must be on the right track, okay, that we're beginning to understand something about what's going on. Okay, right. Okay, so let me end by telling you that feedback isn't always negative, okay? So far, we're driving the gas out to make the big galaxies red, okay? That's been the goal, to reconcile the theory with the data. But now we're finding something really weird as we look in the early universe. We're finding star formation is much more effective at high redshift than we ever dreamed it could be. And I want to show you what that might mean, okay? And that might mean that basically these outflows, if they run into dense clouds, can compress the clouds and actually help them make stars. And because the outflows are moving so fast, this is a much more rapid way of driving star formation than just simple gravitational motions, bicircular motions, as normally occurs in the Milky Way, for example. And so basically, all it says is that you can essentially increase star formation by something like the ratio of the outflow velocity to the typical gravitational, the circular velocity in a disk, or the typical random motion, okay? Because the outflow can basically move faster and compress things, overtake more clouds, and boost star formation that way. So that's all that really is. It boosts the pressure. But what I want to do is show you examples of this. So first, in the local universe, we see what we call triggered star formation. Okay, so the examples are really legion, but one of my favorite ones, Centaurus A is great. You see star formation at the ends of the jets. Okay, here are other examples where you have, here's a quasar where you have an outflow and you see indications of star formation at the edge of the outflow. There are more. This is the most classical example of all, called Minkowski's object. You have an old elliptical galaxy with radio jet, which is enveloping, running into a giant gas cloud, which is now forming stars at a prolific rate, a dwarf galaxy called Minkowski's object. So that's triggered star formation, we're pretty sure. Here are the radio contours. And the numbers are legion. So there is another example there, 3C 368, a classic example. And there are examples in dwarf galaxies where you see a black hole in the center, radio contours, enhanced star formation around it. And in this example, it's rather beautiful. You have, from a while ago actually, but you have a quasar with actually detected molecular gas along the jet. Okay, so basically you can enhance one more, okay. Okay, so here's a close-up of one of those examples where you actually have the host galaxy out here, an AGN, outflow, and enhanced star formation over here. Okay, so this you're quenching, and you have both negative feedback and positive feedback at the same time in this object. Okay, here is an example of which tells you how large a problem we're going to have in understanding the high redshift universe. In a survey of radio galaxies at about redshift 4, they found they had to decompose, this is with infrared, far infrared data, and Hubble data, etc., a whole mixture of things. They were able to decompose the data into two stellar populations. One of which is old, at this redshift, it's as old, when it tells you when the galaxy formed, right? The old corresponds to the current old stellar population. But one is very, very young, okay, 30 million years old. And what is amazing is there's roughly equal mass between the old stars and the young stars. So something really efficient happened, and this is a radio galaxy. This certainly had a massive radio jet, etc., which did all this. Okay, so here's another example of the specific star formation rate, which is the ratio of the star formation rate over the mass in stars, inverse time scale. In the Milky Way, it's down here somewhere. As you go back in time, you see star formation becomes more effective. And at high redshift, it seems to level out, except for the fact that when you look at the radio galaxies, it's becoming incredibly high. So this is much higher than we see anywhere in the local universe. So again, suggesting that radio galaxies maybe are playing some role in their outflows, their jets, whatever, enhancing things. Now I'm going to run out of time, so I'm going to skip through one of these. This is another example of radio jets doing their thing. Here's one example which is from the MANGA project, which many of you, I think, are involved in. I thought I'd show you this. So this is a typical example from the prototype program, where in this galaxy with an active nucleus, in the BPT diagram, you see, AGN activity in the center and star formation on the outside, what you expect. But so here's another example, which I would love to understand better. Another galaxy also with something active in the center and a dust lane. And this is its BPT diagram. And so here you see star formation is dark blue, purple, AGN is red. And in this example, you see the opposite. So I think it's a challenge. It could be, and I'm going to show you now a simulation which suggests that this might be positive feedback in action. Okay, so you can take this at face value. I hope this movie works. Okay, so here's a gas-rich disk galaxy. Okay, and here's the AGN shooting out a jet. But it runs into gas, it develops this bow shock. You see the bow shock? Which is overpressured and it's going to affect the... Okay, so I thought that would happen.
So the colors are gas density, right?
Yes, this one is pressure. I know, sorry about this. My computer it's a beautiful simulation. I want to try to show it to you, but I have an old computer which is not doing very well with these things.
Perhaps here, if you can.
Over here?
Perhaps the PowerPoint frozen.
Yeah.
Can I?
Good luck. Should we just get out of it? No, I think we have to get. No, I don't think that's the problem. I think you can see it happening on the screen there.
Yeah.
Let me get out of PowerPoint. I don't know how to do this. No,
No,
it's PowerPoint. Yeah, I'm sorry, but it's frozen somehow, so I'm going to have to reopen it maybe.
You will launch again the PowerPoint.
Yeah.
Let me see. That was like your last slide, right?
Yeah, it's basically my last slide, right?
There it is.
Okay, so we're going to watch the density again and cross our fingers that what you're going to see on the right is the pressure, and on the top right, the stars. So that's what is the magic about this, but and after this, I'll give you my conclusion. So basically, note the bow shock is going to compress the disk, and it's going to induce star formation. So is this going to happen automatically? Yes, good. Okay. So I won't touch the computer. This is a pressure wave, basically. This is a pressure contours. So the gas-rich disk is being squeezed. And with any luck, we're going to see the stars. Okay, so these are the old stars forming in the galaxy. And then at 12 million years, we turn on the jet. And so there's lots of gas, so you're making new stars. So you're driving the gas out of this is a kiloparsec or so across. You're driving the gas out, you've got a ring of stars, okay? So that's another signature of positive feedback. And the final thing I just wanted to say is that in the velocity dispersion, because you're pushing these clouds, which are already making stars and maybe even making new stars, if you look in detail at the velocities, you find a region where the velocities acquire significant non-circular velocities, or excess radial velocities, because of the disturbance from the out of the plane of symmetry of the galaxies. Okay, so my final slide is this: there are major issues in galaxy formation. We don't know what drives star formation in detail, why the efficiency is so low. We have conjectures, we have models. What quenches star formation, feedback, AGN feedback, how the AGN outflows even couple. Many assumptions are made, even the simulations I showed you. What drives the turbulence, its effects, etc. This is on kiloparsec scales, which we're beginning to resolve now in the simulations, but these are the questions we really need to answer. At larger scales, what's the significance of the clumpiness we seem to see? What about bulge formation? How can that be suppressed? What explains the high specific star formation rates? How effectively do the AGN couple again? And then where are the baryons on larger scales? What are the mixing? Where are the dwarf galaxies? And what are the role on larger scales of all these things? Okay, so I would say then there's no consensus on any of these, and there's a lot more to do, so thank you.
Hello. Questions?
So in your last simulation, the star formation region that increased was between two shocks, right? So you
Yes,
have the
yes,
pressure from
exactly,
both
that's
shocks?
right, yeah.
Okay. Could it be possible to have it like outside of the galaxy, like in the part where the shock is pushing, like not in between both of the shocks, but in one of the fronts?
That's right, I would think so, sure. If there's gas outside, then if it's a wind, for example, that was a jet I showed you. So if there's a wind, that would, have a much wider opening angle and push the gas against what it's, yeah.
Thank you.
It would be very similar in its effect on star formation, but different geometry. Yeah.
Okay, I have a question about the image that you use in manga with this manga galaxy.
Yes.
That you see the region about AGN and star forming.
Yeah.
Okay, it's interesting to plot also the maps of equivalent with it of the line that is using in the VPT
Yes.
diagram,
Yes.
because you need to also consider that at the outskirts of the galaxies, in manga galaxy also, you have a low signal to noise.
Yes.
And then maybe the star formation, well, the AGN emission and the outskirts, it's maybe because you have low signal, and then it's in a spurious detection that is not exactly a physical meaning.
Yeah, that's an interesting point. I'd like to. That should be demonstrated.
Okay.
More questions, comments? In Ensenada, do you have questions, comments? We can't hear you.
You can see you.
One question.
Go ahead.
Hi, Joe. This is Miguel. Joe, has this positive feedback been observed in simulations like the Aquarius or the Eagle?
No, it has not been observed by them because I don't think they've put in the right physics to even set it up properly. So right now, very few simulations, essentially none of the zoom-in simulations, cosmological simulations, have this physics in.
And what about semi-analytical models? Has anybody tried to include them?
People are trying now, yeah. So there's still rather little out there, but there are 2 or 3 groups doing this.
Okay, more questions, comments? Okay.
Hi. Well, I would like to ask you about something you said yesterday. Why do you think that the modified gravity is not a good solution for the problem?
Right, so I had a slide on that, so let me show you the slide on modified gravity. So I think it'll explain why immediately. So this was just to say that when we haven't found dark matter because we're not looking in the right place. So let me just make that point and answer your question as well. So this is the cross-section we think the dark matter might have and its mass. And we've looked in one very tiny region. There's all this other space that we have not explored yet. So who knows, the fact that we haven't found it may not be a problem. But as for modified gravity, I think this is the real problem. We have all of these theories of modified gravity. They're all addressing the dark energy problem at some level. None of them can explain dark matter. And so as far as I know, there's not a single dark matter theory that consistently can account for dark matter. That's the problem. We need some new ideas, perhaps, but all of these theories, you can see they're all listed by various, from scalar tensor on down, and including the latest emergent gravity theories. All of those have been highly criticized as, they simply cannot account for dark matter, I see.
We have a question over here. Hi. Is there some kind of rough estimate as to the ratio between the positive and negative feedback, in the sense as to how much worse does the problem get?
Well, I think it's very hard to see positive feedback because that means you have lots of star formation and there's an AGN doing something that might have begun things. It's a bit like a chicken and egg problem. So maybe it's better to ask what is the time sequence. So if there is positive feedback, I think it's the first effect of the AGN. But then you rapidly induce so much star formation and there's so much AGN power continuing that you drive the gas out and it becomes negative feedback. So it's a transient phase. And as to what the ratio is, it's very, very, very hard to say. It speeds things up, basically. So the time scale it gives you star formation on a shorter time scale and therefore potentially at a greater rate.
Thanks.
More questions, comments by the students? Okay.
Just regarding this comments you're making on whether modified gravity theories can explain dark matter or not, I think there are some F of t gravity theories that, at least in the spherical symmetric limit, can give you the flat rotation curves and even the lensing. We've published a few of them. But also that you haven't got them now doesn't mean that you cannot eventually have them, no?
I agree. I think we need a clever idea. To my knowledge, the theories that do try to explain dark matter have severe problems with cosmology and have been rejected for cosmology-related reasons so far. But I think we're just waiting for the right theory. Perhaps,
Students? Okay.
There are two magic words you have not used. There are magnetic fields. Do they play a role in galaxy formation and all these processes?
I'm sure they do, actually. And I think that that might be part of a solution because they provide extra pressure, which may affect star formation, collapse, etc. I think people are just beginning to play with that as an additional ingredient. But you can see things are already so complex without magnetic fields that it's not clear when you add them whether you'll improve our understanding or it's just adding one more, several more degrees of freedom. So that's the worry at the moment.
Okay, and Ensenada, more questions? No, it looks like...
More questions here?
Okay.
No, I don't see any.
Okay, thanks. And the last question?
Okay, Joe, I think I will disagree with you regarding over here.
Oh, sorry.
I think I will disagree with you regarding probably it's just the terminology, the problems that you mentioned. I think most of them are not problems, are just controversies. Because all this, the cusp core problem, the too big to fail, these kind of problems, in fact, depend on the observations. I think the observations are not yet in the status of constraints very well these things. So before to claim that this is really an issue, this is really a problem, I think we need to advance more in the observations, which really I think is a problem, or an open problem, let's say, is the missing baryons. This is really a very, very intense. Where are the baryons? Why we see the baryons as ratio 3 in the Lyman alpha clouds, and today most of baryons are not seen. So this is really, I think, and for me it's a problem, an open problem. And the others, I think, are just controversies. So I don't know. It's just my...
No, I agree with you, basically. But the thing that worries me most is that whenever one of these other things I call problems come up, one of the standard responses are it's the observations are wrong somehow. It's an observational issue. Maybe the dwarf galaxies have some inclination that we haven't accounted for, et cetera, et cetera. So the fact that you have so many problems that all of them you have to say are due to the observers is possibly a little unfair. But we need more data. That is absolutely that's for sure. Yeah.
Compare observation with theory adequately. Yeah.
Okay, so we now have the small presentations by the students and the postdocs, and then we will move to the after special colloquium. We will have snacks and all that. Bueno. Ok. Abraham, ¿cómo pongo el HDMI aquí? No, ya lo tengo conectado, pero para el proyector, por favor. Van a tener 2 minutos y les voy a presentar esto cuando les falten 30 segundos. Esto cuando les falten 5 segundos. Y esto cuando ya no me hayan hecho caso, ¿ok? ¿Cómo? Son 2 minutos. I think I mentioned that in my email. Okay, well, try to do it in 2 minutes.
Thank you. Well, my name is Emma, and I'm working here as a postdoc. Well, I'd like to talk, to tell you a little bit about my work. My research is focused on the galactic halo, and in particular the stellar populations and their chemistry. And this is all about because in past decades the investigations point to 2 different halos in terms of chemistry and kinematics, and it may be due to different star formation processes. So, well, my work started inspired by the work of Nissen and Schuster 2010 that found 2 different chemical trends in the alpha to iron versus iron to hydrogen space. And they found a high alpha population of stars with a flat trend and another with a decreasing trend with the iron abundance. And they interpreted these results as if the high alpha population was formed in an environment with a higher star formation rate, and the other population with lower alpha to iron ratios in an environment with a lower star formation rate, and thus with the contribution of supernova 1A. So inspecting in a larger sample of stars, and well, and not restricted to a local volume, we found these 2 populations that are very clear in for magnesium to iron as a function of the iron to hydrogen abundances, but also for other alpha elements. And what we are doing now is trying to to infer from these 2 populations some parameters related to the star formation history. Well, from the observations, the observed alpha to iron ratios, theoretical yields for supernovae 2 and 1A stars, and a chemical evolution model with the help of Letizia Carigi. And we are still working on it because we can't find agreement between the abundances of the different elements. But for example, the most 5 seconds. Okay. Well, that it seems that, for example, the top left panel, right panel, show the efficiency, and it's different for the 2 populations. So well, it's all.
Well, I study the kinematics and the star formation in luminous infrared galaxies, because as Joseph Silk said yesterday, we derived the laws of star formation in the nearby universe for earlier times, and then one first a better approximation is to study the luminous infrared galaxies in the nearby universe, because the star formation in the peak in the peak epoch of the star formation was mainly in the infrared. So studying these galaxies can help us to understand the star formation at early epochs. So here I show you two plots. On the left is we cannot see anything, but the y-axis is the surface density of the star formation rate versus the star formation rate for several samples of galaxies. So in the pink ones are normal star forming galaxies, and the rest are nearby extreme environments as luminous infrared galaxies and the antennae galaxy, which is almost a luminous infrared galaxy. And this is traced by the H alpha. And on the right is the y-axis is the molecular gas surface density versus the molecular gas mass. And what we see is that in the luminous infrared galaxies, compared to normal star-forming galaxies and the Milky Way, there are more dense star-forming regions in the molecular clouds and in the star formation rate. I have to say that the identifications are independent. They are not the same regions. They just trace the peaks of the H alpha and the molecular gas. Well, the good thing is that, or one way to study the star formation rate is also taking into account the turbulence of the velocity dispersion, because a lot of time is forgotten or is not taken into account. So these observations were made to study also the kinematics. And I show you just because I just have time to show for the molecular clouds or the giant molecular clouds associations. And what we see is that the turbulence enhanced the molecular gas surface density. Here is the molecular gas surface density versus the velocity dispersion, and for the LIRGs, for the luminous infrared galaxies and the antennae galaxies, the density is higher or is enhanced. And here is the size of the molecular clouds versus the velocity dispersion, and these regions are the normal star-forming regions and in the galaxy and in normal star-forming galaxies, and these regions where we see that they are more massive, like between 6 or 7 and 10 to the 6 and 10 to the 9 solar masses in just molecular gas. So my idea is, I'm going to finish really quick. My idea is that this region from here, they are very, very massive. And I think that the feedback here is less efficient, and that's the reason that why they are more dense and more massive. But also, I wanted to say something more, but yes. Well, yes, but the self-gravity is what it drives this big velocity dispersion. And I was just wanted to ask Joseph, what do we need for a robust star formation law? And what about the turbulence? But you mentioned before, but I don't know if you have some comment.
We can discuss the lunch.
My name is Eric. My PhD project is related with the story kinematics and dynamics of galaxies to test the cosmology. With the recent or the new generation of surveys, we have homogeneous and statistical representative samples to do this study. This kind of surveys have several advantages. For example, we can resolve properties of galaxies. For example, the kinematics where we can evaluate if galaxies are perturbed, or it show inflow or outflow. There are very well-known scaling relation as Tully-Fisher for late-type galaxies, or Faber-Jackson for early-type galaxies, where the intensity scatter and slope have important information about the dark matter rule in galaxy formation and evolution, information about stellar population encrypted in the initial mass function, information about the dynamical state of galaxies. with Khalifa and manga data using optical tracers, Hasacha alpha and stellar kinematics, we infer our version of Tully-Fisher relation using the 20% width of the velocity of histogram, similar to the H1 profile, and also infer the Faber-Jackson relation and the scary relation that is the combination of rotational velocity and velocity dispersion for all type of galaxies. In a subsample of 35 galaxies, we solve the kinematics in order to get the maximum velocity, and found that the scatter decreased in a factor on 2 in comparative with the velocity histogram. Our final goal on our study is infer or the velocity, the circular velocity function for dark matter halos, which can be translated to halo mass function in order to compare with the robust prediction of the lambda cool dark matter scenarios. And my last slide is to show the kinematics about this galaxy that show ionization in the inner parts due to stellar formation. And I analyzed the kinematics. I removed the rotational velocity and found this kind of residuals that could be outflow or inflow that, yeah, I find that could activate the star formation in the inner parts.
My name is Ruben Calete, and I work with Vladimir Avila and Aldo Rodriguez. And I work, my PhD work is aimed to some empirical models. What is this basically? Well, I would like to start just saying that having a model or that can describe the formation and evolutions of structures, such as is named the lambda CDM, and can be, well, we can obtain information through computers, through cosmological simulations with big volumes, high spatial resolutions, and information regarding the properties, the evolution, and the statistics of the so-called dark matter halos. Just an example, I put here the Bolshoi simulation and the result of Aldo Rodriguez from last year, which is basically how is the distribution as a function of mass, the number distribution of halos, dark matter halos as a function of mass for different epochs. Well, aside of that, we have also information regarding the observations, such as the distribution of galaxies as a function of stellar mass, or the two-point correlation functions, or star formation rates as a function of stellar mass. And also, these observations are not limited only to, are also segregated into broad galaxy populations, blue and red galaxies, which is very important. And here also another observations, which are, well, these are the results from my master's degree thesis, where I compiled radio observations, radio of follow-up observations of radio from I forgot how to translate it. Follow-up observations of radio, selecting from galaxies selected by luminosity or in the optical. And basically, if you have a distribution of properties of halos and distribution of properties of galaxies, the way that we can connect these properties, halos and these two, the galaxies with the halos, is through in a statistical way. And these are basically having distributions of properties of halos and galaxies. We can connect through these. These are the halo abundance matching, the halo occupational distribution. These are several statistical ways to connect galaxies and halos. Just as an example, to my colleagues, the abundance matching technique, if you have two distributions observed, one's the galaxy stellar mass function and the dark matter halo mass function, which is the distribution in the simulations, you can connect them just assuming that in each dark matter halo leaves a galaxy, you can just connect in an easy way. Yeah, okay. You can connect the properties such as mass. This is just how can we. Well, basically you can connect, and I was going to explain the evolution. How can we connect the statistically the evolution? And this is a preliminary result.
Hello, my name is Chandrachani. I'm working with the Auditorio in the n-body simulation for the alternative model. But today I took the opportunity to discuss about my previous work with my formal advisor, which about the Bayesian comparison, model comparison for some of the non-standard cosmology using the supernova data, recent supernova data, and the BAO. So it is about this Bayesian analysis. It's inferred to two ways. Either you use to constrain the parameters, or we can use to infer to do the model comparison. So in this work, we choose some of the cosmological models, which is listed out in the table 1, which we consider some constant parameter, the scalar field, and we also consider the interacting model, which is described. Yeah, these are all like a scalar field model. This is like the interacting model. We also consider the FR model, which is kind of power law, which is like a modified gravity, and DGP is like a brain motivated models. So we took this kinds of all models. They have their common parameters, free parameters, and we have their own free parameters as well. So what we took is we consider, I said, as mentioned, we use about the recent supernova observation, which is 740, and within the redshift range of this, and the BAO is about 9 data. So what about this Bayesian model selection is about we need to provide some prior informations about the model parameters, and we calculate the likelihood, and we compare different model, but reference point we use the lambda serium as our reference point, and we calculate this bias factor. So what is the conclusion from the bias factor is like when we have the bias factor ratio, which is ln of this, it's high about 5, then it is very disfavor, and if it is about 0.5, it's moderate, and it is about less than 1, it is like inconclusive. You cannot say anything about the models, it is favorable, or we can't say anything. So when we do this analysis, we do the Monte Carlo chance analysis, and what we found in the result is like that. This is from the GLA, which is only the supernova. So what we found is almost all are inconclusive. We cannot tell anything about they are favorable or not with the supernova. But when we combine with the BAO, we find that this DGP model it's completely ruled out, but rays are still inconclusive, so we cannot say anything they are good or not. So almost I'm finished. So this is the representation of the result. So you can see that this is combined, the black one. Blue one is for the GLA, which is the supernova. So almost one model is ruled out when combining. So I just would like to suggest what the difficulty part we are here is it's not enough. Yes, the data is not enough, and we have still a lot of models, and they are more similar to lambda serium. And the methodology, it is good enough or not? Thank you.
Well, I guess that. Okay, so I guess that we can move to that part of the auditorium. So we can grab some sandwiches or something and discuss about the projects and the talk. Okay? Thank you.
Thanks.
Gracias a los de Ensenada.
Thanks, bye. Hasta luego.